Good morning, dear students. This is Dr. Ishwarlal. We are going to discuss discrete mathematics of the course. The topics are partial order relations and Hasse diagram. This comes under section 6. So, this before going to partial order relation and Hasse diagrams, first we are go what is the objectives of the course and aim of these sessions and what we have to learn from these concepts. So, these are comes under the instruction objectives, learning outcomes before starting the concepts. Instructional objectives which we are designed here to understand partial order set, to understand the structure of Hasse diagram. Coming to the outlines, what outcomes of the section, identify the partial order sets, design and draw the Hasse diagrams. Okay, depending on the different posets what we are given, that we have to able to draw the Hasse diagrams. Now, first of all, we just go a small introduction on posets. Poset means partial order sets. Partial ordered set means a set is said to be partial order set if the relation is developed on the set under certain properties. What are their properties are? The first property, they satisfy the reflexive property, or we call reflexive relation. Okay, that means that a set which have a relation on the set with some symbol denoted by R, such R should be satisfied on a set for every element in three properties, that are first one reflexive relation, second one antisymmetric relation, and third one transitive relation. See, if any relation satisfied on the given non-empty set under these three conditions, then we call the pair, the set and relation is called a poset. So, dear students, that is a poset is a one type of ordering on the sets which follow the three conditions. See, what are the importance of the partial order sets? So, there are so many importance. In mathematics, we have lattice theory, topology, algebra. They developed a basic concepts under the posets. Some of the topics which we learn in higher algebras, Boolean algebra and universal algebra, this comes under the posets basic. So, all the ring structures and developing the partial orderings and groups structures, these all comes under the partial order set with the binary relation. So, this is one type of mathematical application what we studied. Not only that is the mathematical application, we go to the another side in the artificial intelligence and biological science and anywhere where in decision making problems and operational research, we are certainly use the ordering the sets which will be follow how we are going to optimize and how we design the properties and studies in the artificial intelligence to learning relations among the concepts and rules and facts which already there, and also the biological consent relations between two pairs by using this partial order relation. Okay, and also further a network analysis also very important. Regularity depends on direct analytic graphs also. So, these comes under all partial order relations. So, that's a very important. So, before going to the partial order sets, first we learn basic definition. What is that? I told just now, a partial order set is poset, shortly we call poset, a set with relation, a non-empty set S and a relation R. I already shown here that should satisfy relation, three relations properties: reflexive relation, antisymmetric relation, transitive relation. That is, A related to A for every A for S on S. That is, the element, every element should be satisfy the relation. And antisymmetric, if A related to B and B related to A, because vice versa use, if both the that relation happens under these elements, then we have to show that two elements should be same. So then that property is called antisymmetric property. And if come to the third property, transitive property, if A related to B and B related to C, that gives the A related to C, then the property comes under transitive property. If these three properties satisfied relation on a given set, then the pair set and relation pair is called a partial order set, and this order is called partial order. So this make a note important, this is the partial order sets. Okay, so comes under the some mathematical symbolically we show the partial order sets. We just write first letter P and you just assign a relation is less than or equal to, that is symbol, mathematical symbol, you know, less than or equal to, greater than or equal to, these are the symbols. Using the symbols instead of a relation R, x less than or equal to x for every x in P, that property called reflexive relation. X related to y and y related to x, x is equal to y, antisymmetric. Here the relation comes less than or equal to, x less than or equal to y and y less than or equal to x implies x is equal to y. And coming to the third property, x less than or equal to y and y less than or equal to x, if you show x less than or equal to z, the property comes under transitive. So if the satisfied the less than or equal to on the set, given set, then P less than or equal to, then P less than or equal to, this pair is called a poset. Dear student, instead of taking R and a set S, we construct like this a non-empty set P, and with the relation mathematical symbol less than or equal to, we construct like this poset which satisfied these three conditions, then the pair is called a poset. Like that, if you see the change this symbol, the dual symbol, what is the duality of less than or equal to, greater than or equal to, the same set becomes the partial order set by with the dual nature of less than or equal to. We can also see the pair set P greater than or equal to is a poset. So with this we will go to some comparable. Comparable elements means how we compare. Compare means if two elements, if it a integers, suppose A and B, if A less and B big, means we related compare to or equal, A less than or equal to B or B less than or equal to A. With these two, any these two happen, otherwise that should be equal. Any comparable or equal that comes under in the set partial ordering, A less than or equal to B means A is small, B is big, and or B less than or equal to A, B is small and A is big. So comparable elements, these two like this. This type of notation, writing any two elements with less than or equal to, such relation is called comparable, and that we say that the elements are comparable. If they are not comparable, you simply say incomparable. Okay, and further, if you come, why the necessity of comparability in the partial order set? If all elements in a poset are comparable with less than or equal to or greater than or equal to, comparable means either less than or equal to or greater than or equal to, then the poset becomes the chain. That is important. Okay, poset in which every elements are comparable. So that is called chain. That is very, very important. Next, coming to upper bound and least upper bound. Upper bound means the element should be greatest in this set is called upper bound. Among the greatest upper bounds, which one is least, called least upper bound. Like that, lower bound and greatest lower bound. Lower bound among all lower bounds, and which is the greatest one, that is called greatest lower bound. So that's why the posets have both greatest lower bound and see we call the least upper bound. So these two happens, then we say that a poset P is bounded set. Bounded set. So this is also an important. In a poset, every elements are comparable, then the poset is called chain. In a poset that exists both greatest lower bound and least upper bound, the poset is called bounded. These the different properties of posets which we have to know when we are going to study about the partial order sets. Okay. Now come to the how we can construct a partial order set, whether given set with some relation is a partial order set. So come to the, I taken here the integer set. See, integers high to already given in the test what form. See, roster form 1 minus 0 1 2 3 minus 1 minus 2 minus 3, and that is integer set. Come to the that what is the relation here? Greater than or equal to. Now we have to show that set I greater than or equal to is a poset. The first property already we discussed, now the reflexive property, x greater than or equal to x for all x in I, and antisymmetric property, x greater than or equal to y and y greater than or equal to x, then x is equal to y. That is a usual number system that two elements are comparable dually, then the two elements are the same. So the property is satisfied by the greater than or equal to relation. And one more condition what we left, transitive property. Let x greater than or equal to y and y greater than or equal to z, then x greater than or equal to z for all x comma y comma z in I. Hence this set what I define I, the integers and the relation greater than or equal to, the pair becomes the partial order set. Like that you have to verify for a set and relation on the what relation is given, whether satisfy these three conditions or not. So I think dear students, you understood how we can verify that the pair set and relation is a partial order set or not. Like that we can go one more example. Okay. Now come to the with here that partial ordering on the positive integer set, and instead of greater than or equal to, here the divisibility is the relation. So with the divisibility we can show this is reflexive. See how A divides A, so that is a reflexive for every element itself a divisibility. So antisymmetric in divisibility rule, A divides B and B divides A, then automatically the two elements should be same, and therefore that's why we are taking A is equal to B. Come to the transitive property, if A divides B and B divides C, 3 for 3 elements in A, then we can get A divides B is B is equal to some quotient Ka, and B divides C means that C is equal to some quotient JB. Coming to C is equal to JB, here C is equal to JB what we taken, and instead of B we taken Ka, and C is equal to JK, this is some integer with A, this comes to under the what, A divides C. So what we have proved, A divides B and B divides C, then we have proved A divides C. So this rule is transitive rule under divisibility. So like that the divisibility is transitive, means that set n and divisibility is a poset. Now come to the set inclusion ordering. This set inclusion order also power set. Power set means the set of all subsets of S is called a power set. What is the less than or equal to? That is a set inclusion order. So a poset, P poset means we have to understood in mind set with relation. This set is a power set and relation is a set inclusion. The pair is called poset. Whence again satisfy these three properties. Reflexive property means under this relation A less than or equal to A for every set in a power set A, okay, that A should be in the power set. So every set itself is a subset. That's why A is subset of A for every A. Antisymmetric, what you already know, A subset of B, if you take A B subset of A also, then in set theory the two A subset of B and B subset of B happen, then must there equality exists, A is equal to B for A, B sets in a power set S. Now come to the transitive property, A subset of B and B subset of C, then automatically that A subset of C for all A, B, C in a power set. So that means that the power set P of S under the set inclusion, the pair is called a poset. So like this, students, the different examples we can verify like this. Okay, I think student you understood what is meant by a poset and what are the properties should be satisfied by the poset under given the certain conditions. Okay, now like that some of the examples are there, you can verify for our exercise. So another problem here given, provide an example of partial ordering R is a set of real numbers. Just you check it, set of real numbers under less than or equal to relation whether a poset or not. So and also I given a finite set X is equal to ABC, with just now I explained with power set, with the ABC you construct a power set of X and P of X and verify that is a partial order set or not. So this gives to you idea and the basic knowledge about poset. Okay, now come to the, now we are go to the next topic which connected to poset. Now first just now we studied about poset. Now what the idea whether the poset you can represent in terms of diagram. Once we have the poset, you have you can construct a diagram or not. So for that yes, we can construct a diagram. That diagrams are called Hasse diagram. The first mathematician Hasse developed diagrams of a posets, but there is some conditions are there before going to diagram. What are their conditions? First, that should be the poset set should be finite. The poset should be finite poset. That finite poset means the poset contains finite number of elements and the relation R should be on the set S. Suppose S is there. Okay, that is a finite poset. And in the set they exist least element and greatest element. And also we use the some rules to draw the Hasse diagram. The elements should be drawn by just dotted or circle, small circles like as shown in this. Okay, and that lines should be relation. Lines should be relation between the elements of a poset. So with this we can get the idea how to draw, how to represent a poset in terms of diagram. Okay, so the first condition, the poset should be finite, contains finite number of elements, relation should be defined, well defined, and we first collect the least element and greatest element you can identify from the poset, then start that bubbling or circling the elements what are there given in the poset, and the lines, connect the lines by the relation what defined on the poset. So with this we can get the Hasse diagram of different dimensions. For example, we go to come to this poset 1, 2, 3, 4, 5, 6. So what is the relation? Less than or equal to. That means, see what is the least element here? Least in the set 1. Okay, greatest element is 6. I think you know 6, 1. Now what is the relation? Less than or equal to. Now you develop a relation. 1 less than 1 is a just go to circle. 1 less than or equal to 2. 2 less than or equal to 3. 3 less than or equal to 4. 4 less than or equal to 5. 5 less than or equal to 6. So if you draw, you get the chain 1, 2, 3, 4, 5, 6. Chain 6 to 1 to 6. This is 2, 3, 4, 5. That means 1 less than equal to 2 less than equal to 3 less than equal to 4 less than equal to 5, 5 less than equal to. This means every elements are comparable. So just now I told chain, in a poset every elements are comparable, then poset is called a chain. So this is the chain. Like that, see diagram also like chain, we already know. So such type of diagrams we can construct by poset. Very good idea by using the poset. But here what are the conditions I explained? The poset should be finite, the relation they developed on that, and first you identify the least element and the greatest element. Then you set the relation should be lines, elements should be dotted, small circles. Okay, like that you can draw the diagrams by using posets. Such diagrams are called Hasse diagram. Okay, dear students, now go to the another problem. See, draw the Hasse diagram of P2, 1, 2, 3, 4, 5, 6. Okay, what is the relation here? A relation A less than equal to B, relation nothing but A divides B. A divides B means use the relation. A should be divide B. Use this. What are the least element here? 1. So 1 divides, 1 divides, 1 divides. What are the divides? 1 divides 2, 1 divides 3, 1 divides 5. According, select elements 2, 3, 5. Come to the 2 divides 4. 2 divides 4 and only element greatest one 6. So 2 divides 6, 3 divides 6. This is the diagram, Hasse diagram. See what I am saying, that dots, see circles, small circles are elements. The lines are relation, that should satisfy divisibility. 2 must divide 4, 2 must divide 6, that's why line is there. See 4 divides 6, no, that's why line is not connected. Like this you have to identify carefully when you are drawing the diagram by using poset. See, posets are finite sets. So come to the a good example, sets, power set. Just now I explained power set. See, I taken 3 elements set. Okay, so write all power set elements. I think a set contains 3 elements, the power set contains 2 cube elements. A set contains n elements, the power set contains 2 power n elements. That's why set contains 3 elements, the power set contains 2 cube, 8 elements. Now what are the least element here? 5. What is the greatest element here? X itself or P itself, 1, 2, 3. So draw the first, start with 5 and just what is the set inclusion? What here it told that set inclusion. Set inclusion means subset. See, 5 is subset of singleton 1, singleton 2, singleton 3, and 1, 2, 1 singleton, 2 singleton is subset of 1, 2, and 2, 3 is subset of 2, 3 set, and 1, 3 is subset of 1, 3 set individual. So all this total set is 1, 2, 3 big set, and this one is subset. Like this we can draw the diagram by using this what you given points in or elements in the power set, and that dotted lines are elements. See, this is pi is small set connected to 1 subset, connected to 2 subset, connected to 2, and 1 is not subset of 2, that's why there is no line. See, 1 and 2 is subsets of 1, 2. Like that 2 and 3 is subset of 2, 3. 1 and 3 is subset of 1, 3, and all are subset of 1, 2, 3. Like this construction. So this is actually Boolean algebra. This becomes the Boolean algebra, very good example for our contest. Okay. So like this we can construct the diagrams by using poset. Once you look posets, that's all sets should be finite and there should be a relation well defined. Okay, dear students, I hope that you understood how to construct this the Hasse diagram from the given set. See, this is the set of divisors of 30. The divisors of 30 already seen. 1, 2, 3, 5, 6, 10, 15 and 30 divisors. See what I told, 1 take least element first, highest element is 30. 1, what is the divisors mean? 1 divides 2, 1 divides 3, 1 divides 5, 2 divides 6, 3 divides 6, 3 divides 5, 5 divides 15, 2 divides 10, 5 divides 10. All are great. 6 divides 10 and 15 divides 10 and 10 divides. See, use this is a poset because among them there is a relation. 1 divides 1, 2 divides 10, all are reflexive property over and reflexive property over antisymmetric. See, any two elements A divides B and B divides A, we can show A is equal to same elements only, represent the antisymmetry. And transitive 1 divides 2, 1 divides 2, 2 and 2 divides 6, that implies 1 divides 6. So, all are coming that transitive properties. That is why diagram itself represents the poset. If you understand the diagram, we can get the poset definition. Like that, you have to construct the Hasse diagram by using posets. Okay, dear students, I hope that you are all familiar and how to construct diagrams from the poset and what are the posets. So, summary is, see, posets we are discussed in this session 6. Summary, what is meant by set, relation and poset, definitions, reflexive, antisymmetric, transitive property, and the pair becomes a poset. After that, how you can convert and into the diagram by a poset. The conditions what discussed is, the poset should be finite and relation should be defined and least element and greatest element should be identified, and first you write a small circles elements of poset, connected lines are should be relation. So, with this you can understood the section 6. Thank you. Very good morning to all dear students. Okay, right.